Very good afternoon, dear faculty members. As I request, please inform your colleagues to join the session. We have just 36 participants. So we'll start exactly at 3:10. So I request, please inform all of them to join the session. Good afternoon, Vipul. I think we can start for the day, sir. Is I'm audible, Vipul, sir?
Yeah, yeah. So,
Yeah.
good afternoon, everyone. Yes, so we are moving ahead. Yeah, yesterday we have discussed a lot for the normalizing conditions and for unitary operations. We have to search for the unity operations. That unity operations we have in the form of gates, quantum gates, right? When this search was going on, 1 minute. Yes. So when this search was going on for the unitary operator, then the search was also going on for the unitary matrices. That matrices were found somewhere from the physics, somewhere from the hardcore mathematics. So like that, and we have formed several gates in the journey of our quantum computation. Now we are starting the gate we have covered. Now we are starting from the concept of quantum circuits. Right? So all these quantum circuits, some of the important things we have discussed: normalization, reversibility, and some part of the measurement. Now only what we have to discuss. So there are two of quantum circuits, just like a normal ordinary circuit in the classical computation. There are series circuit and there are parallel circuits, right? So first I want to discuss about some important uh, properties of the quantum circuits which are not found in the classical circuits, right? So the very first important property is the quantum circuit are acyclic. Acyclic means there is no feedback. So no feedback, no loop, no direct transfer from output to the input, as we were allowed in the classical circuits. So if you have gone a lot in the classical circuits, the logic gates and or not logic gates, then uh, these logic gates, sequential circuits, non-combining, non-sequential circuits, they are forming registers, they are forming flip-flops. So RS, JK, so they are flip-flops. All these flip-flops, in some flip-flops, we were using feedback. In the classical, we were using feedback also. For what? For giving some portion of the output, some fraction, we can say, suppose uh, Q. Q fraction input. Then this input is combined with this is input 2, this input is combined in input 1, and then finally it was working like a JK flip-flop and all these things. So all flip-flops are basically working on these things, but this is absent in the quantum circuits. We cannot go and do a feedback reversibility into the inputs. So direct feedback is not allowed in pure quantum evolution. Okay, so I will tell you the reason later on. And this evaluation proceed always and always in a forward direction. That is, it cannot be go in a reverse direction. Although circuit is reversible, but this evaluation proceed in the forward direction. Okay. So this was a different concept, and the studies was a different concept. The reversibility we can adopt, but on a one circuit it can go in a forward direction. So you can combine these two concepts. So reversibility, if you want to take the reversibility, that is also we have to take along the forward direction. Okay. So this is the one important aspect of the quantum circuits. So quantum circuits are of two types: series and parallel. Obviously, as everywhere there is a circuit. Circuits are of two types: series, parallel. So the quantum circuit will be also of the two types: series and parallel circuits. So Then the second important aspect is yes. So there is no fan in and no fan out is allowed. And this direct results from a unitary operation. Okay. So there is no one to many, there is no many to one. Okay. Just like in logic gates, in the classical computation, we were allowed in the classical computer and the logic gates, these things are allowed. Logic gates, these things are allowed. What these things are, just like the AND gate. Suppose this is the AND gate. AND gate is a two input gate. This is the input 1, this is input 2. AND gate is a two input gate and we are getting a single output for the AND gate. Sorry, single output for the AND gate. Just like that, NOR gate also, OR gate also. So OR gate is also like this. We are having a two inputs having a one output. So this is kind of situation, we will call it many to one. Many to one. So no many to one, many bits to one bit, no many qubits to one qubit. No, it is not allowed here. Okay. Why it is not allowed? It is not allowed, and reverse versa also, vice versa also. Okay. So that means if there is a one circuit, one qubit, so you are not allowed to reduce two outputs from here, as you are doing in a JK and all these flip flops and registers. So from one to many is not allowed. One to many is also not allowed. Is not allowed in quantum. Many to one is also not allowed in quantum. Okay. The reason being is that we have chosen a unitary operation. Okay. Because of this unitary operation, we have to keep the mapping one to one. If we are not keeping this, our unitary condition will different. When the unity will go on difference, then there is a normalizing condition will go on difference. And when normalizing condition go on different, then our normalizing condition were referring to the probability. Our probability is going with one is no longer remain constant. Okay. So that's why these things are not allowed in the quantum. There is some drawback for this. Okay. But with this drawback, there is many more advantages in the quantum circuits. Okay. So no cloning, I will tell you. So the quantum states cannot be copied. These two things are consequence of measurement. Okay. This is the consequence of measurement. Measurement. 1 minute. Let me clear everything. Yes. So these two are the consequence of measurement. Okay. So fan in many to one, one to many is not allowed. Fan out is also not allowed. That is one qubit to one many. Okay. So fan these are called the fan in and fan out. So these are not allowed in the quantum. No fan in, no fan out. Okay. So secondly, the reason is we are taking a measurement here, and the measurement in the classical is different and the quantum is different. In the classical, when we are measuring the things, we are not going to disturb the system. And it is so much important, so much important advantage it's giving us in the quantum. That measurement is itself disturbing the system. So when we are going to measure something, suppose we have coded A, suppose A is in some form we have coded, P is in some form we have coded like that. Okay. And when we are going to measure this system, and going to measure the system, then we have to disturb the system A also, we have to disturb the system B also. So when we are going to disturb the system A, System A will not no longer be remain as it is. It may be like this. It may be like this. Okay. This system B will also no longer remain as it is maybe like this. I don't know. At randomly, I'm withdrawing these things only for the giving the idea how measurement can change the things. So, because of this principle, that measurement is going to change the our original system also. So, without changing the disturbing the system, we cannot measure. So, this property is looking like on a one front, it is looking like a disadvantages, but on this front, it is very advantageous. So that whenever nobody can copy your information, so your original quantum state A and B nobody can copy, because to copy it has to go for the measurement of this system. So when it is going on the measurement of the system, they has to disturb the system. And when they are going to disturb, so originality will no longer remain there. So whenever somebody is trying to copy them, they will not copy. Okay, so this is the advantage of the quantum technology. So 1 minute, please. Yes. So that means this is called the no cloning theorem. So nobody can try to clone your information, and nobody can steal the information in the quantum technology. So this technology is based on the measurement principle, which itself says whenever something is going to measure, we can change it. Okay, we can change. So that's it. So this is the important aspect of the quantum circuits. So when the quantum circuits are implemented, so nobody can do the cloning in the quantum circuits. Second important property is that yes. So the quantum circuits are reversible. That I told you many times. So every quantum gate has an inverse. So this also comes from the unitary transformation. Unitary transformation, we have seen that U dagger is equal to 1. Knowingly, so we are imparting the reversibility knowingly. Okay. So why we want to impart? It is having a very advantage, because I am from the hardware side. I'm just basically I was doing some hardware ready for the quantum circuits. So the quantum photonic devices I have worked, and that's why I can say the advantage. So I am seeing this advantage whenever we are going to build a circuit in the classical chip designing. What we are doing, if in a classical chip designing, if we want the information is going from S1 to S2, suppose, okay, from this bus, and from S1 to S2, we have given them 4 buses. Bus 1, bus 2, bus 3, bus 4. 1, 2, 3, 4, right? So when these 4 buses we have imparted to the S1 to S2 transition. S1 to S2 transition means I'm writing it means I'm also changing the state. Okay. So that means the transition is going on. So this transformation take place to the buses. Right. Now, if we want to reverse the thing, that is S2 to S1, then again we required 4 different buses, 4 different paths. So the extra buses we required, because I am from the hardware side also, so I know this. Okay. So the extra buses are required. We have to take the provision in the circuits to provide the extra buses, or to provide the extra path. But the reversibility provides an additional advantage to us that if there is a, we have connected a path bus 1, bus 2 from circuit S1 to S2. So what is the advantage? So if this bus is taking a work from carrying the information from S1 to S2, the same bus will be used in the same time, will be used to carry the information from S2 to S1 because reversibility is allowed. Because the reversibility is allowed, so just we can re-reverse or retrace the path which we had originally covered, which is not possible in the classical circuits. Okay, and this because of this unitary transformation, this we have discussed a lot in yesterday's talk. So the unity transformation ensures the reversibility. Information is never destroyed in the closed system. This also we have conversed a lot yesterday. The normalization remains constant. So that ensures the reversibility and that impart, this I'm telling my experience, this impart the additional advantage to the quantum circuits for the hardware engineers. Okay. So this is the important property of the quantum circuits. Moving ahead. Yeah. So this also we have discussed. The qubits are neither created nor destroyed. The information cannot be leaked. Okay. So the number of input qubits equal to the number of output qubit. It is inherited in the very first characteristics of the quantum circuit. Okay. So the and all these. Yeah. Now, now coming to the measurement of the qubit. So when we are measuring the qubit, we are measuring the probability. This also we have discussed, everything we have covered yesterday. So in the measuring of the qubit, the probability of measuring a cat zero qubit is coming into the alpha. But since we know that this is for Schrodinger equation result, psi, it is a complex quantity. So mod psi square, it will give us the probability. Okay, so just like that. So if we want to take the probability, we have to make a square of it. Okay, so if just like cat one, we have to take the probability square of that. Okay, and this is called the normalizing condition. We have discussed a lot. Yes, that is very important characteristics. So what is this? Hmm. So the measurement produces the classical outputs. See, the measurements. I will discriminate the classical and quantum. Okay. In the classical, we know we have started this series from prediction. It is very predictable. It is very sure. Okay. So there is no concept of probability. There is no concept of probability in classical world or classical physics or classical computation. Everything is sure. If I am saying that this particle of this human being, this person A is at point this, so it is 100% it is at point this. But in quantum, we are saying we are not sure. We are not sure. That means we are dealing with the probability. When we are dealing with the probability, that means if we are saying that any person is standing here, any person is standing here, so it is not 100% standing here. Always remember. If we will say classically in your daily life, if we are saying classically, if the person is there, if I am saying that my mobile is on table, the 100% classically, this is the classical statement that my mobile is there in the table. And the quantum statement, the quantum analogy of this statement is this: the why there is a 99.9% or there is a 93% or there is a 83% possibility of my mobile is there at the table, kept at the table. Okay, so we are dealing with the probability, and because the probability is large, that's why we are we can say that it is at the table. So just like that, now what is the difference between the measurement in the classical? In measurement in classical gives us sure things. Measurement in quantum, because the quantum lies in the probability. So when we are measuring, we are getting a certain probable outcome. So now, before measurement, as we were discussing that wave and particle, before measurement, the light is in both the form, wave and particles, so in probabilistic nature. But after measurement, as soon as we have gone for the measurement, we have arrived at, to some phenomena, we have arrived that, yeah, light is a wave. To some phenomena, we have arrived at the uh, surety that light, it is a particle. Okay, is a particle. So when we are measuring, so after the measurement, we are becoming very sure that it is a particle or it is a wave. So when we are becoming sure, it means the quantum, after the measurement, the quantum measurement produces a classical output. So output is always classical. The circuit may be quantum, but the output is always classical. Okay, so let's move ahead. So these are all the summarized results for that. No cloning, no fan-in, reversibility. Measurement gives the classical results. Now, the quantum gates in series. So when suppose quantum gates in series, that means we have to start from the input. So there is the input, okay, and in this input we have to apply the quantum gate. Now, suppose two gates we are applying in series. Suppose there are two gates, X gate and Y gate. Suppose there are two gates which is we are applying in series. Everybody knows that we can take the example of resistor. Everybody knows that this is a series combination of resistor. Series means one, the output of one is connected to the input of another. Like that. So output of this one is connected to the input of another. This is a series arrangement. Okay. If something is not science background, then this sentence is for them. So the series arrangement means output of one is connected to the input of other. Okay, this is a series arrangements. Okay, so just like that, this is a gate which is a series arrangement. Okay, and if in this series arrangement, let's clear all these things. So in this series arrangements, if we are doing input, so at the here, if we are giving an input and at the end we are taking a output, right? So how to do these things? Okay. So when we want to calculate these type of things, so we know that input can be a 0 and 1 or a mixed state. So let's calculate first for 0 and 1. Then we can extend this concept to the mixed state. Okay. So how to calculate in the series? So calculation is always from the right to left order. Always remember the calculation is always from the right to left order. Okay. So suppose in this it is given like that there is a A gate, there is a B gate. Okay. Then right to left from here to here, then here to here. Why from right to left? Because the input is always acting at the left, and the very first gate which will operate the input is of this one. So we have to take this operation first. So we have to take this operation first. Then we will take and apply this operator. Gate is operator, right? That's why I'm saying. First we will apply the operator A on this input, then we will apply the operator B on the whole input. That is, first we have applied, this is a, we have applied the operator, we have applied the operator on the input, we are getting a output. suppose getting a psi, this is the output. Then this psi 1 again will apply on the B, psi 1 again apply on the B, and we will get the final psi 2. Okay, like that. We can calculate. So for example, suppose I am taking X and Y gates, then how to calculate these things in series? Then how to calculate these things in series? Suppose this is the X gate, this is the Y gate, and here we are applying suppose gate 0. Okay, and we want to take the output now. Now, how to calculate? So, what we have to do from right to left, that is y, then x, operator x, and then of this x operator is operated on x. Right? So, first we will calculate this one. So, when x is operated on 0, x is operated on get 0. So we got the result. We have the result. So when x is operated on 0, we are getting a 1. Okay, get 1 like that. And if you want to do mathematical operations, then we have this. What we have get 0, we are having 1 0. Then matrix operation of x, we are having 0 1 1 0. Then we can go on the multiplication like this, like this. Sorry. This and this to this and this to this. We were having some multiplication at here. Then whatever the result we are getting at here, we will apply the same result to Y matrix, Y gate. So suppose this is the result. We are getting a result in the matrix form. Then we will apply this result into the Y matrix. Always, we are also having I minus I like that. Then we will see do multiplication for this, and we will get the final matrix in the final form. So like that, we can operate and we can have sequences and mathematical calculations according to the circuit to solve and reach out the final output. This is the final output in the matrix form. Okay. If cat1 is applying, then you can do the same. Okay. So like that, this is the series circuit. So this is the important thing. So the gate multiplies in reverse order of application. So if this is this thing, so it multiplies like that. Okay. Here the order is matters. See here, if instead of instead of calculating this one, see instead of this, if we will place this one before, then it will be typical because we know the rule of the matrix row by column. So when we will place this in place, then it will be a very typical one. Okay. So always the matrix multiplication is not commutative. Always remember. Okay. So to solve the circuits, always remember that because the circuits are in the form of the gates are the unitary operators, and operators are dealing in the matrix form, and matrix is non-commutative. Okay. So always clearly have the precaution to do the things in the right order. So this is not the this is not academic point of view. I'm telling you, when somebody is going for the industrial point of view, so the corporate sector always it is being remembered. So in my hardware side, if I'm applying these things, these logics in the hardware, then it will get a huge blunder mistake in it, and result will be something very interesting. Okay, so this is the quantum circuits. In series circuit, we can multiply like that. Okay, now we coming for the yes. So this we have seen. Now quantum gates in parallel. So when we are going for the quantum gates in parallel, suppose parallel combination means everybody knows if we are talking about the register, this is a register. There are two ends, A and B. So parallel means if there is a register, then both ends we can join C and D. Then both ends we can join like this. Then we can have a common terminal. So this is called parallel arrangement. So like that, if we will replace this like in the gates, so if there is a one gate, suppose X, there is a one gate, another gate is a Y, there is another gate Y. Okay. So always remember in the parallel, wherever in the series circuit, we are only doing multiplications in the matrices. Okay. So in the series, we are doing the multiplications in the matrix. There is X, there is Y. So Y multiplication in the input, then X. Or we are taking X first, then what we are doing multiplication of X matrix to this matrix. Then again we are doing multiplication of this matrix to the resultant of this matrix. Right? So there is only and only inner product we can say. There is a multiplication simple. But whenever the parallel concept is coming, in the parallel concept, always remember we have to take the tensor product. The rule will be same. We have to take from right to left. Operation we have to take from right to left. But we have to take the parallel, we have to take the tensor product in this. So if this is a circuit, we are applying, suppose we are applying CAT 0 here, we are applying CAT 1 here, suppose, okay, then the output, how to calculate? So first we have to go from right to left. So right to left, if we will go, then it means this is the first. Then this is the second. It is coming in parallel. These are in parallel. I can make a parallel symbol. So these are in parallel. So Y gate is parallel to the X gate. That means we have to do the tensor product between X and Y. And the tensor product, we can know the resultant output at here. Okay. The tensor product will be the also the vector. So there is a resultant output at here. Suppose we are representing by a capital X. Okay. Now among these strings, these two, we will also go for the tensor because this is also parallel. So there is very good mistaken things, misunderstanding that we will not go on the tensor product here because these are the inputs. But no. So these are the inputs, but they are in parallel. Okay. So input means basically it is a matrix. Basically, principle, it is also a matrix. Okay. So when don't see now it is a gate or something. These are the matrix. This is matrix 1. This is matrix 2. And we have to do the tensor product of matrix 1 and matrix 2. This is matrix 1. This is also matrix 2. We have to go to the matrix. Okay. So that means matrix product 1. Go for the tensor product. Matrix product 2. Like this. We will have this thing. Then there is we can say 3 and 4. Okay. If things are repeating, the metric 3, tensor product, metric 4, like this, and going on. Then it is also tensor product, it is also one product, it is also one product. Suppose we can say a capital P, we can suppose a capital Q, then we can multiply these and we can get the final result. Okay. So These are some characteristics of the quantum gates in series and quantum gates in parallel. Yeah, there is one more operation which is very much important to calculate the quantum circuits. How to calculate the quantum circuits? So that calculation make it easy. We are not we, but the scientists, the researchers have made one concept. What the concept is? Concept of NOP gate. NOP gate. So NOP is the no operation gate. It is the no operation gate. Okay. So NOP gate is the no operation gate, and no operation means because gate is just like a matrix operator. Operator is just like a matrix, and the no functioning of the matrix. How we can do? We can do by a unique method that a matrix will be a unitary matrix. Okay, a unit matrix. Okay, so for that unit matrix, the representation we are taking I, and that I will work as a no operating gate. Okay, so if all the components are one, like that, okay, so the diagonal is one, it means this is a unit matrix. So unit matrix perform, if we will multiply this unit matrix to the matrix A, we will get again a A. This is the matrix concept. Okay, because the diagonal elements are one. So it will do nothing. So nothing means no operation gate. Why it is very important? It is very important if we are getting, suppose the circuit like this. Suppose there is a circuit with X gate and there is no circuit here. There is a cat 0, there cat 1. Okay. Suppose I am taking Y gate here and there is one more Z gate is operating. This type of circuit is there. Okay. Then, yes, now you can very easily understand that this we can very easily go for the tensor product of X and Y. This we can very easily go for the tensor product. Tensor product of X and Y, tensor product of 0, 1. But at here, how to build, because these are the two inputs circuit. So how to handle? So to handle this one, to make it very easy, we can do without assuming anything, but that will be, yeah, that will be complicated. But to make it very easy, in this same pattern, to make it the symmetry, what we can do, we can assume the no operation gate at here. Because it is a direct circuit or direct wire, so that means there is a no operation gate, we can assume it here. Then we can go for the tensor product. And this no operation gate matrix we know like that. Okay. Then we can tensor product this one. Then this resultant matrix we will get matrix 1. It is where we can get the matrix 2. It is we can get the matrix 3. Then we can multiply. Multiplying this first hit to hit, then multiply the resultant of this to this. Okay. Then following this way, we can solve the circuit very easily. So these are the quantum circuits we are following. So this no operation gate is very much important. Okay. Now the algorithm. Okay. But before going to the algorithm, let us discuss about some implementation of these gates. Uh, Harvard gate, X gate, Y gate in the Qiskit programming. So just wait for a minute, and then I will be ready for the Python Jupyter environment. So give me 2 minutes so that I can open that environment. Utility. Yes. So, see these quantum circuits, we are going to build upon Jupyter environment. It's a Python-based environment. Everybody knows it's a library. And uh, these qubit circuits, actually the hardware is rarely present. So tomorrow we will talk about the hardware developments and how we can implement these things to the hardware. But I can say till that the hardware is very rare, and only there are very few places where the this quantum hardware is being building. So IBM is one of them. It is they are providing the real hardware site to do the research of these quantum circuits, implement the quantum circuits. But that earlier, before 6 months, that was free, but now they are charging the fee on their platform. Suppose if some researcher or some student is making a quantum circuit and he want that this quantum circuit is working in practical, then he has to go for the IBM or there is another platform, Sirag. So Google is also developing the quantum computer, and so its name is Google Sirag. So uh, to the Google, but Google has not facility. So IBM is providing this facility. So for the practical purpose, so yesterday also somebody was talking about theory. So always, yeah, we are providing a Qiskit, but Qiskit is not the practical. In case of quantum, in case of the quantum, Qiskit is only providing you the simulation, only the simulation. It is not the practical thing. So we cannot have an idea that how efficiently our circuit will work or not, because in this what we are going to perform at here in the Qiskit. So Qiskit is nothing, only just an environment. Okay. So the IBM has created some of the tools, some of the libraries, and in the name of Qiskit. So, but it is running in the Python coding. So if somebody knows the Python, there is nothing in the Qiskit. Okay. So it is also, so yeah, what I'm talking about, also a theoretical simulation. We are going to do it here. Uh, Theoretical simulation will always result as we are instructing them. Okay. The theoretical simulation is always resulting as we are instructing them. As far as we are not going for the any quantum computing hardware to run our circuits, we cannot be sure about our new R&D or new circuits. Okay, because I am from the hardware side, I have to run a lot of the foreign devices that we are placing towards here and there. So in Bangalore also there is one startup QPi who is working for the superconducting qubits, and they are making the quantum computer hardware also. And in recent times, recent 3 or 4 months, after the quantum mission has been launched, a lot of faculties are writing the projects on that so that they can be funded through them. And it's a very good opportunity for all the faculties that they can write the project, they can take the funding, and can invent their time in the hardware development as well as for the software development. So this is so okay. Let's now do the some coding in the Qiskit. So in this, a very first step, what we are doing, as we have said that Qiskit is nothing. It is only the platform it is providing. So we have to import some of the things in the Qiskit. So I have installed the Qiskit environment in my Jupyter lab, and after installing, 1 minute, I have suppose I want this quantum circuits. So I am importing the quantum circuit. Then not only the quantum circuit. So this, see, I think you may be 1 minute. Mm, Yes. Now we have to also import the visualization and histogram at here. So yeah, visualization and histogram. Then also there is a simulator. So also there is a simulator, and one more thing. I am explaining everything. 1 minute. One more thing. If we will not go on the back end, it will run here. Okay. Hmm. So, so the first line, this is a Qiskit line that we are importing a quantum circuit class from the Qiskit. So you can just think of PCB type of things. Okay. So for the classical comparison, I can say you that there is a PCB type where we are fitting the condensers, we are fitting the resistance in it like that, capacitors of that like that. So this PCB design in the classical circuits. So for just like that, this PCB we are importing in the form of quantum circuits. Okay. So 1 minute, let me. So now we will run this. Yes. And to run. So that means, wait for a minute. Yes. So the simulator is ready. Okay. So what we did, we have imported the quantum circuit here. We are also imported the visualization. I will tell you the what the visualization is there. So visualization means visualization tool. Okay. And there is a one plot histogram. Yeah, I know that we have to plot a histogram for this quantum outputs. Because the quantum outputs, always remember the quantum output, because quantum dealing with probability, and we cannot believe on the one run because this is the probability cases. So because these are the probability cases, these are the probability cases, so we cannot believe on one shot. So we are running the circuit in one shot, we cannot believe on it. Okay. So because it is a probable case, it is a probable case which is not suitable. So what we can do to increase the probability, we are running it is for 100 times, 100 shots. We are running for 500 times like that, 500 shots. Or you want to be more sure, run for the 1000 times. Okay. Then, so when we are running for the 500 times, 100 times, 1000 times, it means we have to make the histogram to observe that results. Because the 100 result we are not going to make in the table like that. It cannot be tabulated. Means it can be tabulated, but who has the time to see this tabulation? So only we are seeing the histogram for that. So that's why we are importing. Okay. Now, so this is air simulator. This also we are importing. Okay. So air simulator, what it does, it just now till this point, this is we are importing the circuits. Only we are importing, right? Only we are importing the tools histogram. Only we are importing the visualization. We are importing the air simulator. This is the simulation who will simulate the circuit. Okay. Will run the circuit. Okay. Backend means we have given the choice that run the circuit in backend. Okay. Now this is we are ready. Okay. Now what we have to do? We have to make a circuit. So to make it circuit, yes. To make it circuit, yes. So QC is command for the quantum circuit, and this we are making a Hadamard gate at here, and then we are giving the command measure. If you know the Python, expert in Python, it will be very easy to you. Okay. So this draw two style, MPL and Clifford style. So we have mentioned this style also at here. Okay. So this will give us, so this Q1, one in bracket means the circuit has one qubit, and this qubit by default, it is in cat 0 state. So second line QC1 dot H naught, this implies a Hadamard gate to the qubit number 0. So in Qiskit, always remember the qubit are indexed starting from 0. Okay. So conceptually, this takes the qubit from cat 0 into the superposition state because Hadamard gets to superposition states. Now we are measuring the all. Okay, it will measure and that converts the quantum state into the classical bits because we know that measurement will give us the quantum states. So it has created a circuit only. It has not run. It has only created the circuit. There is a Hadamard gate, and because draw, we have given the command draw. So this draw is in like this, the Hadamard, and this is the oracle, and this is the measurement. Yeah, one more thing that measurement sign in the this is the measurement sign. Okay, whenever we are going to measure measurement size. The second point is that this is the measurement. And second point is that whenever in the quantum circuit, if we are making a single line, it means we are making a circuit. This is a circuit or wire. You can say classical analogy, you can say wire. But when we are making a double line, we are making a double line. It means double lines means at that point we are going to measure. So double line represent the measurement and this symbol is also represent the measurement. So whenever you will see these things, the symbol is the measurement, double line. Oh, sorry, this is the measurement. Okay. So this is the circuit. Now we have to run this circuit. So this diagram has been drawn from MAT library, matplot library. So it's a visual check. We are applying the right gate on the right qubit. Okay. So now what we will do, we will just run the job at the backend and get the result. So for that, we also have to give the command and I'm just writing these commands here and will give the histogram also. So see here, so backend, run the QC1 shots, 1000 shots and get the result and the command get the count. So the 1000 times results that counting is required and as a histogram. Let's see here. The result is 501 times 0 is coming, 523 times 1 is coming and should be because it's a Hadamard gate. Hadamard gate is the superposition of 0 and 1. Hadamard gate is a superposition of 0 and 1. Okay, so it should be. So 501 times it is in 0 state and 523 times it is in 1 state. If we increase the number of count 1000 to 1 lakh or something, then we can eliminate this difference. See this difference. This difference is 501 count. This difference is 523 terms. So this is because it represents the probability or possibility. So here the 0 times 0 probability is coming 501. Its probability is coming 523 out of the 1024 sorts. Okay. So this is the difference. Ideally, this should be 500. So this divided by 2. So it will be 512. I should be, ideally, it should be coming like exactly this one. But since there is a probability, it can go either side. So either this is a 501, this is a 523 sides. Okay. So that is the difference we have to learn. This is the main drawback of the quantum circuits. Because quantum circuit deals with the probability and we have to run the different sorts, multiple sorts for the surety. But on the other hand, there are this drawback is very much less. On the other hand, the computation is very fast. Okay. So if we increase the number of shortcuts here, so we can go on 500 or oh, sorry 5,000, 50,000 like that. We can eliminate the difference between these two. Okay. Then we will redistribute the equal probability there. Okay. So let's clear out drawing. So let's do one more thing. So, okay, we can create a quantum circuit for suppose that gate. Okay, then what we can do, job 2, there is a job 1. Yes. So let's create in this cell job 2. So what we are doing at here? So Qiskit 2, this is a quantum circuit 2. So we create a 2-qubit circuit, okay? Because in the bracket, there is a number of qubits. So there is a 2-qubit circuit. So both qubit starts in state 0, cat 0. Always remember that both qubit starts with the cat 0. This is the natural state, okay? So there are 2 qubits, both qubit starts with the cat 0 state, okay? So run job. There is one problem. QC2, we cannot run this. Okay. Okay, let's create another circuit for this. Okay. So let's have a circuit in XYZ gate. Okay. So right here, suppose I'm creating another circuit. Actually, in the last, there is a C here. So comment is coming like this one. Okay. So I have to see there is something like this. So here also we are getting C. So X gate, we are performing, we are getting a 520 times, and we are running these circuits, 512 shots. So in the 512 shots, we are getting always 1. Because the qubit is always, this natural qubit is always in the cat 0 state. Natural qubit is always in the cat 0 state, and we are getting always a cat 1. And there is a 100% possibility. Okay. Let's see. Suppose for the Z gate, that histogram, yes. So for the Z gate, it is in 0 state. 0 state always comes in a 0. 100% possibility of 512 times. So this This we can always appears to code it in a simulator and run the things, but it is okay for some basic level. We can, I cannot name this as a practical because it's not doing in a uh, real environment. Okay, so it's a simulator, so you can simulate in this Qiskit also. Okay, also it's good for the this purpose. It will create you other things. So now just return to the algorithm part. So these are the parts, these are the things. Now let's start with the algorithm. Hmm. Hmm. Let's share. Oh my God. Okay. Share the quantum algorithm. Yes. Hmm. So let's go ahead with our journey of quantum computation. So that was some demonstration. So how you can program the things and set the uh, quantum gates in the Qiskit environment and see the results whether how we are increasing the number of counts and by changing the quantum gates, what possibilities, what probabilities we are getting here. Okay. It is your, yes, it is your personal simulator. So you can go and perform the simulations, different gates, apply the different gates, and know the result. So for this, for the two or three, I can give you uh, some of the exercise. Or if all of you are having a Jupyter notebook, you can chat me. Everyone having a Jupyter notebook? Can you access right now? Okay. So can you access right now? Okay. Good. So I can give you some sort of 1 minute. Let's let's perform some of the tasks on the cascade. So I'm writing some of the exercises. I will 1 minute. I will give you these exercises after the workshop. Then at 5 p.m. I will give you the exercise. You can perform on your own and can we can discuss these things on tomorrow. Till then, we can move ahead. Okay. So, for, yeah, we were discussing about the quantum algorithm. So, let's move with the journey with the same pace. We have discussed the quantum circuits, we discussed the normalization, we have discussed the operators, And we were also going to the timeline method. Okay. So we have said that in 1981, the Feynman has given a spark. The Feynman has given a spark for the quantum computing, that why not we are calculating the quantum, why cannot we can simulate, not computing. Feynman has given the idea to simulate. Why we cannot simulate the molecular atomic and molecular physics simulation on the quantum simulation. So from 1981 to 1985, because this Finland was given this dense idea in the conference, and at that time the conference was very, very rare. There is no idea of internet and anything. So that was not that era. So this was published in the some proceedings of that conference. I have that paper, and from that conference, a lot of scientific communities had evolved this sentence that why cannot simulate the atomic things? Okay, and that the same time there was a deuce. Okay, so he was a physicist. Basically, he is a theoretical physicist who was working on the quantum field theory. So when he was working on the quantum field theory, so he has developed a concept of quantum Turing machine. He has given the concept of quantum Turing machine. So I will tell you one thing, that the classical computers were also based on Alan Turing machine. If some faculties are knowing that, although it was a very long back ago, nobody nowadays are studying this Turing method or Turing machine or Turing thesis. So it was a long ago, 1931, Alan Turing has given the concept of Turing machine. It was a theoretical concept. On that Turing machine concept, our modern classical computation has been developed. It has given the idea of computation. It has given the idea of computation. And this Alan was the first man who was saying and differentiating that computation is a real mathematical problem, different from math. Okay. So, so based on this idea, the computation idea is worked, and in 1950, when at least 1946, then 1946 to 50, when the real hardware is being made, and then this theoretical Turing machine has been converted into the circuit model. Circuit model. Okay. So this theoretical idea, so don't deviate from the theory. Okay. So the idea of first birth in your mind, the mind is always a theoretical thing. So when the idea is have taken the birth in the mind, that then your actions are being taken place from your mind. That is the ideas coming from the theory. So the classical computation is built up when the hardware has come. So this is the story of classical computation. In 1931, Alan has given some Turing machine concept of Turing machine definition of computation. Then definition is came into the reality when are we were having a hardware models, tubes, semiconductors, and all that. Okay. So vacuum tubes, vacuum valves we are having in the age of 1946. After 1915, there was a birth of semiconductor. Then we got semiconducting models. Okay. So then when the hardware is coming, we have explored the hardware, then it just changes. Turing machine concept was changes to the circuit model. Then we made the circuits and all that computers, classical things. Just like that. Now just see the analogy here. So just like that, at here, analogy. Just see. So in 19, just here in 1981, Finwan gave this spark, right? Finwan gave this spark. Then in 1985, one scientist, Deuce, was working on the quantum field theory, and he showed that he said that okay, there is a classical Turing machine, and why cannot be there is a class quantum Turing machine? So he has given the idea of quantum Turing machine. Okay. So this quantum Turing machine, he has given the idea, okay, there will be a quantum Turing machine, or you can say in the Alan has given the concept of tape in the Turing machine. Some of the faculties may be remembering tape had in the Turing machine, right? So these concept and measurement, read the head. Okay. So these only quantum Turing machine, only he has to replace these concept with the quantum gates. Head means logics, that is have to convert for the superposition. Only he has, this is because this Turing machine is a theoretical Turing machine. So this Deuce has given the idea of quantum Turing machine. Okay. But after giving this idea of quantum Turing machine, Deuce itself thinking, Deuce itself thinking that is this quantum Turing machine is really having a good efficiency? Is it really working model? It can be or not? Only this was a question. It can be a really working model or not. So to prove this supremacy, to prove this quantum Turing machine supremacy over the classical supremacy, the Deuce has itself solved one problem. So when he solved this one problem, that the aim was that to prove the quantum supremacy, to prove the quantum supremacy. Okay. So to prove the quantum supremacy, he has taken up one problem. How to prove the quantum supremacy? If classically somebody is taking a 5 steps to solve the problem. Okay. Let me delete all these things. So if classically somebody, the problem is taking the steps of 5, suppose 5 steps. And is it possible in the quantum Turing machine, through the concept of quantum Turing machine, can we solve in a 2 step or less than 5 steps? If yes, then quantum supremacy is proved. If no, then there is no existence, no benefit, right? So actually, what was happening in 1970 to 1980? What was happening? The more computational problems were evolving, just like NP problem, P and NP problems. Okay, all these computational problems. So there is one more that is called uh, complexity. The complexity problems were also evolving in that duration, 1980, 70 to 80 duration. So there was a complexity problem, exponential complexity is there, logarithmic complexity, okay, quadratic complexity is there, like that. So there was the complexity problem, big O problem, big O problem, big O omega problem. So all that problems are coming in that time, 1970 to 1980. Okay. So Deuce also compared these things, has taken the idea from these problems that can be solved with a lesser step. So can be solved with a lesser step. So if it is, then it will be beneficial. If it is not, then there is significance of this. Okay. So being taken the aim of that, Deuce has designed one trial problem. This is called a trial problem. Okay. Because this is a very kidding problem. Okay. It's a there is no application. Just see there is no application. There is no application of this algorithm except it to prove that quantum supremacy. Okay. So the problem was now we are moving towards the context has been developed. Now we are moving towards the Deuce algorithm. Okay. So here, how I have told you how this Deuce algorithm has been made. So Deuce has thinking of quantum Turing machine, and by thinking, he want to prove the quantum supremacy. So the quantum supremacy he has proven with this problem. Okay. So the problem was, see, the problem was uh, this determines. So there is a mathematical problem. Let me delete all the things. So there is a mathematical problem. So suppose there is a function. So function can be of various types. So he has taken the two different functions. So he has taken that is either this function is a constant function or this function is a balanced function. Okay. He has taken this problem only. Various type of functions, repeating function, oscillating function, non-oscillating function, periodic functions. Okay. But, but among that category, there are two more functions. Either this function is a constant or a balance. Here they have checked. Okay. He has taken one problem. He has picked up this problem that we have to check this is constant function or not, balanced function or not. Okay. So the constant function is that to every, suppose x is having a 9 inputs, suppose 10, we have to take a suppose uh, integral. So 10 inputs, it is the value of x, we are having 10, like 2, 3, 5, 7, like this. Okay. So we know that there is a mapping. For every x, there will be a fx value. Every x, there will be a output. This is the input, this is the output, right? For every x, there will be output. So if they are having 10 inputs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 inputs, right? If there are 10 inputs, then then there will be 10 outputs at here, at here, at here, at here, at here, like that. There will be 10 outputs. Now he has to check that if the function is constant, then no matter whatever be the inputs, if the function is constant, these all have the single value, same value, either 5, 6, 7, or whatever. Okay, it is having a single value. Okay, but if the constant function is balanced, so if there is a 10 inputs, so for the 5 inputs, the function's value is same, something else. And for the remaining five inputs, the function value is something else. Will be same. It will be same. It will be same at here. Okay. So this was the problem. He has taken this problem, although it has no significance in the work or application in the daily life. Okay. So this was the problem. So this problem he has solved. He has solved in one step. Okay. So classically, this problem needs two keys. Quantum needs one. So what example I have taken, it will need some 10 queries. Here, this is something else. Here we are taking a 0 and 1. Here I am only taking an example to elaborate you. But initially they have 0 and 1, two inputs. Okay. So suppose if we're talking about this, my example. So if there are 10, so classically to check whether this is a constant or balanced function, you need to check for every input. You need to check for every input. If you are lefting or you are leaving any input, it means you are not able to check whether the function is constant or balanced. Because suppose if you are leaving this input, okay, then if your function value is coming constant, then even then you have to check this also, whether this coming the same value constant or not. So that means you have to invest the 10 steps in classically. Okay. But Deuce has proved that If we go quantum mechanically, if we go quantum computationally, then if we can adopt the concept of superposition, if we can adopt the concept of probability and the interference pattern, then we can solve, instead of 10 steps, we can solve this problem in only one step. That's it. Okay? We can solve this problem only in one step. So that's it. So let's clear all the things. I think so. I am able to make it clear that what is the problem. Okay. So I have taken an example. So a lot of people are confusing in this example because they are feeling math is just like a theory. So this representation somewhat is not making very easy impression. It's go less than a second, less than a second it will go in a mind. Okay, because this type of representation it's some first if you are not habitual, so it will not know going in a less than a second. So let us take up one example of that also. So suppose there are 10 vegetables are there. Suppose there are 10 vegetables, vegetable 1, vegetable 2, vegetable 3, vegetable 4, vegetable 5. Suppose there are 5 vegetables are there. Okay. So if there are 5 vegetables, then we have to check which vegetable, we have to check which vegetable is sweet or salty. Okay. Which vegetable is sweet or salty. So if vegetable 1 to 5, classically what we have to check it this one, a test, right? This test. So classically, each vegetable we have to test, then we can define the if it is salty, all if it's sweet, then all are sweet, then if all are salty. So if we are saying a constant may also come in two ways. If all are sweet, it is called a constant function. If all are salty, it is also called a constant function. Why? Because irrespective of the input vegetables 1 to 5 numbers, they are salty. Irrespective of 1 to 5 number, they are sweetie. So constant can also have the two things, either sweet or salty. Now balanced. Now coming to the balanced. Now you are testing. So okay, we have to take actually 6 because balance means equal. So equal means if 5, then there will be 3, 2, or 1 or 4 like that. So 6 I am taking because of equality. So if 4 are coming to sweetie and 3s are coming to sweetie or these 3 are coming to salty, then they are balanced. Okay. So classically we have to test each spoon from each vegetable. Then we can know that the vegetables are sweety or salty or whatever the test, whatever test. But quantum mechanically, what the quantum mechanics is saying that? The quantum mechanics is saying this concept that quantum is saying just take a single bigger spoon, take and take all the things simultaneously from this, from this, from this, from this, from this, from this. All the things take simultaneously, small liquid simultaneously in the one spoon. Okay? And mixed it. No problem. Mix it. Okay? So only one spoon, take all the things from small, make it this mixture and test it. Now test it. In a one shot, they are able to say that is it constant or unbalanced. Okay. So this was the whole soul behind this algorithm. Okay, so the Deuce has designed this algorithm. They have given the quantum circuit for this. Okay, so how to solve this problem? Okay, so quantum circuit he has not given. He has given the concept, so that in one shot he can test and can tell you that, yeah, always remember, he cannot tell that vegetable one is salty, two is sweety, three is salty, four is sweety, like that. He cannot make this individual choices. Okay. But he can this make this choice that it is constant or it is balanced. The overall whole system, he can make choice the whole system, whether the whole system is constant or the whole system is balanced. Okay. So how they can do this? Okay, this is the example I have given for the elaboration, because nobody, most of the people are somewhat restricted to the math only. Okay, and it has no application, so they are not interested in the examples. So my method is always deal with the examples. Okay, so that you can better understand the whole world. So actually, whatever we are doing, whatever we are studying for the betterment of the world. So we have to deal, and software also especially. All the software that is designed to run on the daily life problems. Okay. So whatever is the problem of industry, problem of robotics, problem of clouding, whatever it's the problems of our daily life, from among the daily life. Right. So how can examples be different from the daily life? Okay. So how they are doing this? So they are making one circuit for this. So for speed up. So and yeah, now coming to the original thought. He has taken that this function can take a 0 and 1. Okay. He has taken a one function. This function can take either 0 or 1. X as a X, either 0 or 1. Okay. So we have to check at x is equal to 0 whether the function, what is the value of this function. We have to check at x is equal to 1, what is the value of the function. Okay. So classical computer mean classically it needs two queries. First we have to check for this sentence, then we have to check for this sentence. But he has proven that, I was saying that it is a toy problem. Toy means kids level problem. Okay. So he has taken only two queries, not 9 or 10. I have elaborated to understand better understanding of us. So quantum, he said, but quantum needs only one query. Okay. So it was on the one side, on the one thing, it was not looking so much applicable. But if we will increase this to x is equal to, if we increase x is equal to 100, see, if we increase x is equal to 100, here I am writing, when having only x having only two queries and the quantum is giving in one step, is only half the steps. Okay, quantum is solving in one step. See, this is half of 2. So it is not really beneficial because it is only doing the half things. Okay. But if it is x is in 100 times, 100 queries, even then it has the power to solve in one step only. Okay. It has the power to solve in one step only. Okay. So that is the real application. So how many times it has reduced the efforts? Okay. So later on it is proved, and it is given in the Grover's algorithm and Deuce algorithm, that if there is a n step and type steps, then it can also solve in a one step. Okay, so like that. So yeah. So what is uses? It uses a superposition, and superposition uses, it means when we are coming on the circuit model, we have to use the Hadamard gate. Okay, interference, for the interference we have to use measurement. Okay, so and it demonstrates the parallel evaluation. So what is the parallel evaluation? There was vegetable 1, vegetable 2, vegetable 3, vegetable 4, vegetable 5, vegetable 6. Individually, classically, we have to take individually. Classically, we have to take individually. But quantum, they are taking all of these liquids, small liquid in a one shot, right? So this is called parallel. So parallelly, he is inputting this one in a one shot demonstrating. So this is called parallel evaluation. Okay, it is called parallel evaluation. Okay, at the quantum level. So this is the whole thing. Now we are coming on the circuits. Yeah, yeah. So there is an oracle concept behind this. Okay. So what is the concept of the oracle? Uh, we will review this oracle very deeply in tomorrow's session. But at here, when the oracle is coming, oracle just like a function. Oracle, what is oracle? Oracle is just like a black box. Oracle is just like a black box. Outsider of this black box. So who has built it? Who knows? But what is inside the black box? But for the outsider, this black box is functioning like that. You can give the input, you will take the output. Okay. You don't have to interfere what process is going inside it. Okay, what the process are running, what the equations are running, how the calculations are being going on. No, you don't have to interfere. Only you have to keep in mind, you have to give input, you have to take output. So black box, or this is called a oracle. Okay. So yeah, certainly the builder knows what is the function inside the oracle, what is they are going to produce. Okay. So I also have one example for that. That if suppose in a mall, there is a mall. In a mall, there are a lot of floors, okay, and a lift is there, okay, and so mall builder or mall contractor knows, and administrative staff knows that at first floor there is a clothes shop. On second floor there is a toy shop, okay. On third floor there is something cycle shop. On fourth floor the computer shop. Okay, but the customers are not knowing that who is coming from outside. So the customer who is coming outside, he knows only he insert in the lift and press the button of first floor, second floor, or if you are opening first, second floor, you are spotting like this cycle, this is cycle, this is a toy shop, this is toy, this is something cloth. Okay. So this is functioning like a direct, you direct the customer where he has to go. So customer don't know what is inside the circuit of the lift, what is inside it, written, coding written or not. They knows only they have to press button, it will reach at this one. So give the input and take output. This is function of Oracle. Okay. So the oracle will function at here. Okay. Now coming to the circuit. So what is the how we can do this? What is the circuit for this? So what we will do at here? Hmm. Yes. Share. Here. Share. Yeah. So what we will do at here? At here, uh, we are applying a Hadamard gate in both the inputs. So at here also, we are applying a Hadamard gate. Okay. And this Hadamard gate, the work of the Hadamard gate is to superimpose everything. This zero, so this hero, he is creating a superposition of 0 and 1. This one is creating superposition of 0 minus 1. So what makes a difference between this one and this one? There is a different phase only. It is a superposition of 0 and 1. It is also the superposition of 0 and 1. But it is at different phase. It is at different phase. Okay. It is at different phases. One. Okay. And these different phases has gone on the oracle, and inside the oracle, these two different phases are superimposing on each other. Even these two, suppose this is S1, this is S2, these S1 and S2 are superimposing and interacting with each other. Okay. And on interaction, after the interaction, again, after the interaction, there is a some result coming at it. But that result is the encoded form. So the Hadamard gate, again, we have to apply for the measurement. Because there is a concept of reversibility in the Hadamard gate. In the Hadamard gate, the thing is that cat 0 converts into the positive state. Positive means 0 plus 1. Cat 0 plus cat 1 by root 2. And it is also convert this 1 convert to the negative state. Okay, that is cat 0 minus cat 1 by root 2. Right? So, but since the gates are reversible, so if 0 is converted to the positive state, means superposition state. Positive state means superposition state. Okay. If 0 is converted to the superposition state, then if input is in the form of superposition, so it can also convert into this state or in this state, depending upon the superposition. It will recognize the superposition. It will recognize the superposition. Okay, it will recognize the interference. The interference is positive side or interference is negative side. If the interference is the positive side, it will give us revert back 0. If it is interference in negative side, it will give us revert back to 1. Right? So here the Hadamard gate is also be applied. Okay, let me clear everything. It's beginning to meshy. So Hadamard gate is being applied at the output to determine one of the positive, and then we are going to measure it. So it's a hardcore circuit. Okay. So first prepare cat 0 and cat 1, then apply Hadamard gate, superposition of 0 and 1, then oracle. Oracle means there is some formula for the superposition. Okay. Then Hadamard convert the phase into the measurable. Again, this Hadamard. This is for this Hadamard. This Hadamard converts the phase, because I was talking about if there is a 0 and 1, if there is a positive phase, if there is a negative phase by root 2. That it converts this phase to the measuring possibility. If is this phase, so you can leave it. And you can directly say that if it converts this phase into the 0, this convert this phase into the 1. It's a reversible gate. So it will work in this direction also. Okay. So convert into the measuring probability. And then from the measurement, we can say that is the function constant or balanced. Okay. Then it means that we are having a taking a one query out of two. Only one query we want taking at here. Okay. So that is the working of Deuce algorithm, and Deuce has only demonstrated the importance of quantum supremacy over the classical one. the theory. Okay. So till that time, the 1985, in the 1985, Deuce has given this algorithm. Till that time, there was no hardware to realize. There was no hardware to realize to implement these circuits. Okay. So only that was a theoretical thing at that time. So until the 1990, in 1990, there was so much, plenty of the Deuce has also worked on some other algorithms. So that is called Deuce-Joseph algorithm for the n input. This is for the only two inputs. So this is for only two inputs. For that DJ is for the n inputs. N inputs. There is some more algorithm was there. So this is Bazarani algorithm is working. Simon algorithm. He has worked on different problems. So there are much more algorithms are there who has come theoretically. And circuit has also come in theoretically. Circuit model has come, but theoretically. Okay. So in 1994, this is the very important year for this quantum boom, or we can say eh, quantum bomb, not a so boom bomb, you can say. So in 1994, Shor has arrived, and Shor has given one problem. Shor has worked problem which is called periodic problem. In between of that, there was, yes, this is the Grover. There is a one Grover algorithm is there. So Grover algorithm was there, who has also given the data sorting. Data sorting. So tomorrow we will discuss some of the algorithm, Shor and Grover's that for the data search. Okay. The Shor has given, and they said that the problems can be in the periodic form. If we can solve the periodic problem, then it will show the direct supremacy of the quantum. Okay. So, so this Shor's algorithm, he based on this Shor's algorithm, this is the most important algorithm for our. So every application, whether it's RSA, whether it's encryption, all that application are based on this Shor's periodic problem. Okay. So basically, it was only a factorization problem, but how to convert that factorization into a periodic problem, that is the work of the show. Okay, so that we will see tomorrow with some more concepts on so how this Deuce algorithm is working on the uh, how to work in the Qiskit program, that we can also uh, demo this tomorrow. Okay. So for that's it for the today's session. Okay. And also tomorrow we will study some of the hardware side. Okay. What are the some sorts of the hardware, superconducting qubits, photonic qubits, what are there? So, okay. So any question you can put up on the chat. So I can wait for, I'm waiting for some time for your questions. You can check. Is there any question? Okay. Okay, then goodbye for now. And tomorrow we will move ahead in the quantum computer journey. Okay. Okay, hand over to the Sushmita.
Yeah, thank you, sir. Thank you so much. We'll meet again by tomorrow at 3 p.m. Thank you.
Okay.
Yeah, so dear faculty members, tomorrow is the last day for this particular program. I request please everyone join the session and attend the last day of session. So yeah, attendance link has been shared on chat. I'll be sharing once again. If you have not marked it, kindly mark your attendance. I think we can wind up for the day. Thank you. Thank you for joining. Have a great day.